Hello and welcome to session 3 of a tutorial to Mill Standard 1553. In session 2 we discussed the different message types that make up the communications content of Mill Standard 1553. In this session we'll discuss timing issues described within the specification as well as techniques developed to maximize throughput within the constraints of the spec. Now let's look at some timing-related terms associated with 1553. Later, we'll see what the spec or the industry has to say about them. The time between the end of one message and the beginning of the next message is called the intermessage gap time. The amount of time the remote terminal has to respond to a command word or command word plus data for BC to RT commands before the bus controller regards it as timed out is called the RT response time. In most systems, there is a list of messages that periodically repeats itself. The time of this period is called the major frame time. Many systems divide the major frame time into smaller periods of time. These smaller periods are each of the same duration, but contains different messages during each time period. These smaller periods are called minor frames. The intermessage gap time is defined in the specification as being a minimum of 4 microseconds from mid-parity to mid-sync. We'll look at a graphic of that in a moment. This means that the bus controller may not send out the command words less than 4 microseconds after the last bit of the previous message. It may wait longer than that and very often will. There is often confusion when measuring timing in 1553. This is partly because the terminology changed between Rev A and Rev B of the spec. Rev A measured dead time on the bus, whereas Rev B measures mid-bit to mid-bit. 2 microseconds of dead time are equal to 4 microseconds of mid-bit to mid-bit. The reason the terminology changed was that mid-bit to mid-bit is easier to measure on an oscilloscope. In the above example, there is no difference in the signal of the second half of the parity bit and the beginning of the dead time on the bus, whereas the mid-bit of the parity and mid-bit of the sync are both vertical lines on the scope. The primary method the bus controller has to know that an RT did not receive a command word is by checking for the RT's response. If an RT does not respond, the bus controller would like to move on to the next message as soon as possible. This necessitates defining a timeout value past which, if the RT has not yet responded, the BC assumes it will never respond and may then send out the next message. This value was altered between Rev A and Rev B of the spec from 7 microseconds to 12 microseconds, measured mid-parity bit to mid-sync. The system architect will put together all the messages needed by all the RTs in the system and form a list of messages that must be sent out periodically by the bus controller. The list of messages is called the major frame or bus list, and the period of repetition is called the major frame time. For most projects, it is between 20 and 80 milliseconds. Now let's say we have a critical message, for example, incoming missile alert, a less critical message, perhaps current latitude, and a low priority message, say landing gear safely stored. We would prefer to call the most critical message more frequently than the least critical message. This slide demonstrates how we can divide a 40 millisecond major frame into 4 10 millisecond minor frames so that the critical message A occurs 4 times as often as the non-critical message C. Medium priority message B occurs 3 times within the major frame. To get a better feel for how 1553 is used in a real application, we'll define a realistic scenario and see how it would be handled using the 1553 bus. A pilot wishes to know if a missile is functioning properly. He presses a button to instruct the missile to perform a self-test. The results of the test then appear on the pilot's display. Now let's give names to the various devices in our scenario. The button that the pilot presses to initiate the self-test we'll call RT2. The missile being tested we will call RT3, and the display that the results are reported on we'll call RT4. The bus controller periodically checks the button RT2 to see if it has been pressed by sending an RT to BC message to RT2. RT2 may respond with a data word of 0 to indicate the button has not been pressed, and a data word of 1 to indicate that it has. The bus controller will then send this data word to the missile RT3 using a BC to RT message. If the data word is 1, the missile will perform a self-test. Later, after the missile has had enough time to perform the self-test, the BC will send it an RT to BC message to get the results of the test. Finally, the BC will send a message to the display with the data returned by the missile's RT. One could design the system so that if the RT2 button is not pushed, none of the other messages are sent. This sounds reasonable, but may violate the real-time characteristics of the system. The system must be fast enough to function in a worst-case scenario. There is therefore no point in saving messages in a non-worst-case scenario. It is very important to make sure that various devices are synchronized with each other. For example, if a camera is filming terrain, it is necessary to associate the resulting film or video with the time and place that it was taken. Therefore, the camera, the clock, and the navigation system must all be properly synchronized. Let's look at how a 1553 bus controller can make sure all terminals are properly synchronized. The BC first transmits a broadcast mode code to tell all RTs to set their time tags to 0 or some common value. Since the broadcast command is received by all RTs simultaneously, they synchronize simultaneously. Since RTs do not respond to a broadcast command with a status word, the BC then polls the RTs one at a time to see if they received the broadcast command. One of the mode codes requests the RT to return the last command word received. If this last command received was the broadcast synchronized command, the BC knows that the synchronization was successful. We have now seen some of the timing issues associated with the 1553 bus. In our next session, we will look at some of the hardware elements and characteristics of the bus. If you have any questions or comments, you may find our contact information on our website at www.mil-1553.com. Thank you.